from previous classes where we discussed a lot on nonlinear programming and the strategy we use to solve the problem. It's based on line search. We call line search. Yeah. So, well, the idea is on we formulate the we reformulate the problem by trying by what's it? For example, we start from higher number of the Bayesian variables, and then we transform the problem to a single variable optimization problem. In order to transform from higher number of Bayesian variable or multidimensional variables to single variables problem, we find a suitable direction. Okay, so we specify the direction first, and then from one direction we find an appropriate step length, right? So you see that we have two steps. The first one, we define the direction, and the second one, consequently, we identify optimum step length. Okay, so you see that the new position is updated from current position by direction times with step length. Okay, and then once we obtain new position, new points, we test the new point whether we should stop the algorithm or not, right? So okay, so you see that, for example, the initial point is x1, right? So we find the suitable direction s1. S1 can be what is it? Any direction that leads to better solution. It depends on the algorithm. Some algorithms suggest different direction, but of course those directions point to the new point that has better objective function. Okay, so here we find S1, a new direction, and then you find the new step length in order to obtain new point, right? And then from here we implement again the algorithm by choosing direction and step length. Okay, and then we repeat it. Okay, and we learned about how to find the step length and also how to find the direction. Okay, so any comments, any questions on that?
No, Prof. The only question I have is in a conjugate direction method. So.
Oh, okay. On conjugate. Okay. Yeah, we will quickly move to a new topic, and then once you have any question on any point, then we can discuss. Okay. Well, allow me a few seconds. So I have to change my earphone. 1 moment. Okay, so well, we start from how to find the step length first. Assume that we have direction already, and then yeah, we have several algorithms to find the step length, and for numerical method, of course, yeah, we have two classes of the methods. The first one based on elimination, and the second one is based on interpolation. For elimination method, of course, well, we have to assume that our objective function, I mean transform objective function, it's a unimodal function. Yeah, and based on the what's it property of unimodal function, you know that unimodal function must be well in the window in the window of concern there must be only single minimum point. Okay, assume that we are going to minimize it, and so we can what's it choose a trial points, and then from a few trial points we can capture the shape of objective function. Okay, so yeah, basically if we have a window from A to B, right, the length range from A to B, and then we choose 2 points to evaluate. For example, x1, x2, we choose these 2 points, and then we evaluate the objective function, and we know the property of the unimodal function. We can what's it, reduce, we can eliminate some part of the original area of concern. Okay, so we repeat this algorithm, then we can what's it shrinking. We can shrink down the area of interest to well much smaller. Okay, and then with that specifying small enough window or length, we can define our target minimum point. Okay, and then we can obtain the point that represent the minimum point in that iteration. Okay, and well, then we repeat the algorithm again because, well, of course, as I mentioned to you that we what is it? We determine new direction, right? And then from that direction, we transform the problem again from multi-dimensional to single dimension, single variable, and then we repeat this algorithm. Okay, so we have elimination method, we have heuristic search, we have exhaustive search, dichotomous search, and so on. Many problems, but I show you some algorithm. If you repeat if you check the slide we gave you and repeat the calculation, you will see how we can how can we implement each algorithm. Okay, and from now we move to the direction. Okay, for the direction cost, we have several methods also. We have the algorithm can be our algorithm can be classified based on the information we use in order to determine the direction. The first class is based on gradient. Okay, when we say gradient, that means we use derivative information, regarding the derivative. And the later case is we don't use the derivative, but we use directly the objective function value. Mhm. Okay, so and Kadim asked me about the conjugate direction, right?
Yes, bro.
Yeah, what is your problem? What's your question? What's your question, Kadim?
Okay, I just want to know how the conjugate direction was determined from the example, especially,
From
yeah, from the
from
example.
from the example. Okay.
Yes.
This one, right?
Yes, bro.
You want me to repeat the explanation of this slide?
Yes.
You mean?
Yes.
Okay. Well, we have this problem, this example. We have x1, x2, right? x1 minus x2, and then plus 2x square of x1 plus 2x1 x2 plus square of x2. And wow, for example, if we have s1 and this direction, okay, we define it first this direction, and we want to find a direction which is conjugate with s1. Okay, of course, when we say conjugate direction, we have one direction and we want to find another direction which is a conjugate of the first direction. Of course, if you want to choose different direction, I mean s1, and you determine the conjugate direction for s2, you will get different s2. Okay. Okay. Then we from this one see that we rearrange our objective function, to be like this, in a quadratic form, and then we obtain a, okay, which is matrix of the what's it, quadratic term. Okay, you see that for the quadratic function we have bx, and then we have we arrange our function like this. We have b transpose x plus and the quadratic term. The quadratic term is half of x transpose ax, and then we have to identify this a. Okay, and from this one we use a concept of conjugate function, because we know that for the conjugate function s transpose as must be 0. Okay, this one we said we know this direction is 1 2, right? And we know a from for our objective function, and then we want to find the conjugate direction like this.
Actually, the problem I had was the identification of matrix A.
Mm-hmm.
That's the problem.
You don't know how to arrange the objective function
In this form,
right? Yeah,
yes,
in
bro.
this form. So yeah, it's algebra, in algebraic equation, So what should I tell you? So wow, you can start from the quadratic form first, quadratic term first. Yeah, you rearrange this one first to and well, make sure that you can satisfy the coefficient of the square x1 and square x2. Okay, because this term, I mean square x1, the coefficient of square x1 coefficient of square x2 and also this coefficient of x1, x2 is actually determined by a. Okay, so from this quadratic term, the terms related to quadratic terms, you should identify that first, and then compensate the rest by this linear term. So well, you try it, and you cannot, once you convert it back, you cannot obtain the same function.
Yes, Prof. That was the problem I had, but maybe I will try it again.
Okay, then to try again. Okay. Okay, beside that conjugate function, and of course this the direction, the common direction is this one, right? The what we call it the direction along the axis first. This one, right? Direction 1 0 0 0 1 0 0. Yeah, the rest like this. We go along each dimension. Okay, but this one is easy. Yeah. And what else? We use this concept in Powell methods. Right? Powell's method. And what else? The other, class of algorithm is simplex method. For simplex method, it's very, you see that for simplex method, we don't use derivative at all. So the benefit of this algorithm is because the algorithm does not use gradient. So you see that because we don't use gradients, that means, what's it? No matter the objective function is discrete or continuous, or in some case, the objective function cannot be differentiated. We don't care about it, right? Because we don't use the derivative. We use only the function directly, the objective function directly. Okay. The simplex method. Okay. And the next one is steeper descent. Steeper descent, we use minus gradient as a direction. Okay. This one. Yeah, it's direction. Okay. We have example of the steeper descent method. And this is conjugate gradient again. Fleischer-Reeve method. We start from this steeper descent, and then we update. For the next step, we don't use the steeper descent anymore. We update the steeper descent direction with the previous direction. Okay. Okay, so you see that from previous lectures, you see that we wow, the original problem must be what's it, unconstrained optimization, right? Because we what's it, we have no mechanism to deal with constraint. Okay, we just deal with multidimensional problem by by transform the multi-dimension problem to single variable, right? Multi-variable to single variable, just that. But the original problem must be unconstrained. If we have constraint problem, we cannot solve the constraint problem by using these methods. Okay, do you agree? So, wow, then the problem is, if we have constraint optimization problem, how to do? I mean, constraint nonlinear optimization problem, because if we deal with constraint linear programming, it's all right. You know, linear programming is very easy. Even we have constraint, we know how to deal with it. Or for classical optimization problem, we know how to deal with it using Lagrange, right? Lagrange method or KKT, Courage-Kuhn-Tucker, right? But by using numerical method, we don't have algorithm yet to deal with constraint optimization. So today I will show you how to transform the constraint problem to unconstrained problem. Okay, from constraint optimization problem to constraint optimization to unconstrained optimization problem. Okay, you see that constraint has two effects on our problem. In the first case, the constraint may have no effect at all on the optimum point. When we consider that, well, when we say that the constraint has no effect on the optimum point, is it possible? Yes, it's possible. If the constraint is not active, you see that for nonlinear optimization problem, our optimum point can be the inner point, not on the boundary, right? Not on the boundary, not on the constraint. In that case, you see that the constraint has no effect at all. Okay, because, well, no matter we have constraint or we don't have constraint, but the constraint do not define the optimum point. Okay, this is a very simple case because, well, you don't have to consider the constraint at all. Okay, but you have to make sure first that your constraint does not define, your constraint do not define or do not determine the optimum point. Okay, in this case, the minimum point can be found by making the necessary sufficient condition, right? So we just say that, well, the optimum point is at optimum point, the gradient must be in all direction must be 0, right? And from minimum, the Hessian at that point must be positive, right? So you can guarantee that the minimum point, and you can apply those algorithm, I mean, the linear line search, learn from previous lectures that, well, transform the original problem from multi variables to single variables, and then use, find the step length and then repeat the algorithm, you can solve the problem. Okay, so in this case, as I mentioned, the minimum point can be found by making use of the necessary condition and sufficient conditions. Okay, if you use line search, you can do it, and then you just check the stopping condition. Okay, the condition to terminate the algorithm by just use this necessary and sufficient condition. So okay. Okay, for example, this problem. Well, let's say that this circle. It's a isopropy of our objective function, and you see that it's actually this is the snapshot. I mean the cross section only. So, well, it's a kind of a parabolic. Okay, so the objective function is on the other axis that perpendicular to your screen. Okay, and then you see that the objective function, our objective function, well, this is our isopropy, right? All points on this line, this circle line, yeah, have equal objective function. Also on this line has, yeah, have identical objective function, and the optimum point is here, right? And you see that our constraint is here, this axis and this axis, also this axis and this axis. We have 4 constraints, and you see that our objective function is not defined by the constraints. All constraints are not active. Okay, so once all constraints are not active, I can say that those constraints are inactive. Okay, so you see that this is the first case. Okay, we have nothing to do with the constraint at all because the constraint do not determine the optimum point. Okay, okay, so yeah, let me tell you one important thing, that to use such conditions, you must be certain, ensure that the constraints are not going to have any effect on the minimum. Okay, then you can use necessary condition, sufficient condition to define the constraint. Okay. Okay, and the second case is the optimum solution occurs on the constraint boundary. Okay. In that case, the Courage conductor necessary condition indicates the negative of the gradient must be expressible as a positive linear combination of the gradients of the active constraint. So in that case, for example, we have a constraint here. We have these 4 constraints, and you see that feasible region is only this region, right? This is our feasible region, and this is the shape or contour of our objective function, and you see that without constraint, the objective function, the optimum solution should be here, right? Should be at the center here at this point. However, our constraint, our feasible region doesn't cover this original optimum point. So you see that we have to move back, okay? Go back off from this point to this point, right? Because you see that the direction of the improvement or the gradient of improvement of the objective functions is this direction, right? So you see that we have to back off from this point to this point, back to this point. And the point which is still in the feasible region and has best optimum point is here, this point, okay? And you see that this point is defined by this constraint gi, right? Okay, if we move this constraint, we obtain new optimum point. Okay, and you see that in this case, constraint has strong effect, right? Has effect on the optimum point. Okay, and the third case. Third case is the objective function has two or more unconstrained local minima. The constraint problem may have multiple minima. Okay, for example, we have this feasible region. Okay, this is our feasible region, which is defined by 4 constraints. Okay, and the original optimal objective function has multiple optimum point. For example, this point A and point B here, they have, well, this objective function, this surface contains 2 minima. Okay, this point A and point B, point A and point B, points A and B are both local minimum points. However, the constraint, we have constraint here, and this constraint impose new optimum point. And you see that we have this local minima still exists, right? And we have a new optimum point, which is defined by the constraint. Okay, in this case, this point, this constraint is active. Okay, at this point, we don't have an active constraint at all. Okay, so we have 3 possible cases. And what about the fourth case? We have another case. In the fourth case, the objective function has a single unconstrained minimum, and the constraint may introduce multiple local minima. Okay, the objective function has only 1 local minimum. Okay, and we have constraint here. We have feasible region here. Okay, with this feasible region is, well, we have how many constraints here? We have 5 constraints. Okay, our feasible region is defined by these 5 constraints. Okay, this constraint is not linear. You see that? Let's go. Okay. Anyway, the constraint, well, impose 2 local minima here. Okay, 2 points. This x1 and x2 are both local minimum points. In this case, you see that this point, we have 2 constraints, 2 active constraints, right? And this point too, we have 2 active constraints. Okay, so to solve this problem, well, the easiest one, we can use random search method. For random search method, we generate a trial design vector using 1 variable number for each variable, and then we verify whether the constraints are satisfied at the trial design vector. If we have we violate any constraint, then we regenerate the trial vector again until we obtain the trial vector which can satisfy all the constraints. Okay, and if we can generate the constraint which is can satisfy all the constraints, we can generate the design vector which is can satisfy all the constraints. Okay, we obtain the best design, and then we check if we evaluate the objective function first, and then we regenerate a new point, and then we, of course, the new point generated must satisfy the constraint, and then we compare the new point with, the objective function of new points with the objective function of the best point we obtained previously. Okay, then we can we call it random search, because each time we randomly generate the design vector and then test it. Okay. Okay, so this is the random search method. The other technique is we can transform our objective function to a new objective function by integrating the effect of the constraint. For example, this one, let's say our original optimization problem is fx. Okay, we disturb the original optimization objective function by combining the effect of the inequality constraint and the effect of equality constraint. You see, we have inequality constraint and equality constraint. But the point is on inequality constraint, because we have two possible conditions, right? The first condition is if the point that vector violate the constraint or not. If it violates the constraint, of course we have to include the effect of the violation of the constraint, right? However, in the case we don't have any violation, those design vector, it's in feasible region. That means the constraint has no effect on that. The value of this gx should be 0. Okay, we have two possible cases: 0 or violate, no violation or violation. So we have to we can use the max function. The max function is it compares between the 0 and gj x. So if you don't have a violation at all, it might be 0, right? But however, if there's a violation, so we use this violation, okay, this constraint as a violation, and then we square in order to make it positive, right? Because you don't know whether this one is negative or positive, right? We have to change it to positive. To make it positive, we square. And the last term is effect of equality constraint. Okay, so for equality constraint, our constraint is hx must be 0, right? So if it's not 0, that means that design vector violate the constraint. It can be violated in negative or positive. However, for both negative or positive, those points violate the constraint. So we take square of this to make it positive, right? So no matter hx is negative or hx is positive, we take square, so it must be positive, right? So any questions on the transformation of the objective function from constraint problem to unconstrained problem? No question? Okay. We call it, we call this algorithm as penalty, okay? Penalty function. Okay. It's in class of algorithm. Okay, the other technique we can use to deal with the nonlinear constraint, nonlinear optimization problem, we call it sequential linear programming. For sequential linear programming, the concept is very easy. We have the problem is nonlinear, right? But no problem. We transform, we estimate all the constraint and objective function as linear programming problem. Okay, so that means, well, you approximate all nonlinear function with linear function. Okay, for example, if we look at fx, we select one trial point. Okay, initial point x1, and then at x1 you use Taylor series to approximate the optimization problem. I mean, starting from objective function. Okay, change the objective function to linear function. And for constraint, our constraint also, we change it to linear function. Okay, inequality constraint also, equality constraint also, we change everything to linear function by using the linear term, only linear term of a Taylor series. Okay, and then once we transform all the nonlinear problem to linear problem, then use linear programming to solve for solution. Okay, and we repeat again because you obtain the solution, that means you obtain a new trial point, right? New point. You obtain a new candidate for optimum point. Okay, then we have to check whether we should stop the algorithm or not. If not, then we repeat it by approximate all the function as a linear function. Okay, using a linear term again, Taylor series. Okay, you obtain new point. This is okay? Any questions? Any question? No? Okay. So this is the concept of the sequential linear programming. And the next one is method of feasible direction. Okay, for the method of feasible direction, it's actually similar to the line search. Okay, first we choose a starting point, specifying all the constraints. That means, well, our starting point, initial point, must be in the feasible region. Okay, and then we move to a better point according to iterative scheme. Okay, but for the direction, we have to make sure that our our direction leads to a better solution and still inside the feasible region. Okay, so you see that the underlying algorithm is similar, very similar to ELIZA. Okay, new point is a disturb of the initial point with lambda, which is a what's it? Step size, right? And SI is the direction. Okay, SI is direction of movement, and lambda is the distance of movement or step length. Okay. But the condition we have to check that lambda, the value of lambda is always chosen, so that this new point xi plus 1 lies in the feasible region. Okay, and you learned previously about the search direction is that you can use various algorithm by using different algorithm to determine the direction. Okay, and the direction specified property 1 is called feasible, while direction specified both property 1 and 2 is called usable. Feasible direction. Okay, property 1 is a small move in the direction violate no constraint. Okay, the direction that a small move in such the direction violates no constraint, does not violate any constraint. Okay, and the second property is the value of objective function can be reduced. Okay, because we minimize it. So yeah, that direction should lead should lead to a better solution. Okay, better objective function. Okay. Also, there are many ways of using a usable, feasible direction. Okay. For example, the direction, this feasible direction at point X. Okay. If it satisfies this relation, derivative of this objective function, okay, based on step length, it's S transpose of gradient F at X is lesser than 0, it's negative. Okay. And there's also a new method for another method for a feasible direction. Okay, you can take time to look at it later. And okay, the next algorithm is penalty function. For penalty function, it's similar to what I told you about the transformation of original unconstrained objective function to a new function, okay, including the effect of constraint. Okay. However, in this case, of course, we include the penalty or the effect of the constraint on the original optimization problem. Okay, on the original optimal objective function. Okay, we transform basic optimization problem into alternative formulation. So however, we expand the concept by to transform the unconstrained minimization problem to a new objective function. We have several choice of the function. We can choose the function like, it's a original problem plus RK summation of G. Okay, and then this summation of G, we can use a max function, right? As previously. Or the penalty function formulation for inequality constraint. Well, we can use other function. For example, this kind of function, and this function we actually you can select any function, a possible function, but those possible function can be classified into category. We call it interior and exterior methods. Okay, in the interior formulation, Tj is minus of 1 over G, like this. Okay, or we can use this one, this Tj as a log of negative Tj. Okay, and you see that what is the property of this one? Can anyone tell me? Kadim, can you tell me the property of this inverse of G? Kadim. Kadim is not here. Okay. Saku, are you here?
Yes, John.
Okay. So can you tell me the important property of this function? 1 over G, inverse of G.
I don't know.
Okay. So
Yeah.
you see that G cannot, what happens if G becomes smaller and smaller? If G is smaller, becomes smaller and smaller, what happened to big G? I mean inverse of G.
Yes, it will get increased or large.
Yes, very large, right?
Yeah.
So if it become, it will not be 0, right? Gj
Yeah.
cannot be 0, right? Because this term will be very large, right?
Yes. Yeah.
Okay, so what happened if we penetrate our original problem? I mean, original objective function with the such terms, this term, okay? Inverse of small g. You see that if g close to 0, this term becomes very large, right? So,
Yes.
so you see that if we start from interior point, the initial point which is inside the feasible region, that point through the iteration, you run for many iterations, you will not leave the feasible region. Okay, you will not reach the boundary, you will not reach the constraint. Okay, you will not move close to the constraint. This function trap you inside the feasible region, always inside the feasible region, because once you move close to the constraint, okay, this term will put you back from the constraint. Okay, you got the idea? Remember that G is, well, normally we write that G must be, one moment, positive, right? Must be greater or equal 0, something like that. Okay. Beside this inverse function, that's minus of Gj, we can use this algorithm, log of minus Gj. This function also works the same because you know that where we cannot reach zero. Zero means well, we cannot be on the constraint because log of zeros. Yeah, we cannot find such function. Okay. Besides this, some commonly used form of the function of Gj in the case of exterior penalty function formulations are this one, we use max function, absolute of max function, or yeah, max square of max function. But you know, for this function, max function or square of max function, we can leave the feasible region. Okay. So if the the point can leave the feasible region, that means it's an exterior penalty function because we cannot guarantee that the point we are working with must be inside the feasible region. Okay, so in the interior method, you see that the unconstrained minima of phi lie in the feasible region and converge to the solution as Rk is vary in a particular manner. Okay, Rk is this coefficient. Okay, in the exterior method, the unconstrained minima of the phi k all lie in the feasible region, converge to the design solution from the outside as Rk is changed in a specific manner. Okay, so let me show you a graphic of the concept of the algorithm. This is on the figure A. It's a concept of exterior function. So let's say original objective function is fx, this line, this linear, okay, function. And we have constraint here. Okay, feasible region is on the right hand side, in this region. Okay, on the right hand side of this vertical line, this vertical line is a constraint. Okay, and you know that we disturb our original optimization objective function with other term, right? So in the transform objective function, the original is here, right? This line. In the transform one, we try to bend or penetrate the point. I mean the objective function of the point outside feasible region with some value which is much larger. Okay. So, however, it depends on the in this case it's an exterior function. Once the point violate the constraint, leave the feasible region, we penetrate it. Okay. But the degree of penetration, you know, the degree of penetration depends on the R on this term too. This coefficient. If you use very large R, very large this value, very large value of R, the coefficient. That means, well, the value of the transform objective function will increase significantly once the point leave the feasible region. Okay, here. Okay. If you increase R, you will obtain the function like larger like this. Okay. If it's close to infinity, of course, it go steeply, follow the constraint. Okay, but of course, if we use very large R, large coefficient, the algorithm, most of the algorithm will fail to solve, because here we have a discontinuity. Okay, discontinuity of the objective function will occur at this point, and most of the algorithm which use derivative will stop at this point. Okay, and figure B, for figure B is the interior penalty function. For interior penalty function, like as I mentioned to you, that if we start from any point inside the feasible region, but you see that the point cannot leave the feasible region, because once we come closer, once G come closer to zero, right? The objective function, I mean the transform one, the transform objective function will increase significantly. Okay, so that means the function, I mean the interior penalty function trap the point inside this feasible region only. Okay, any questions? Any questions? Oh, sorry. Okay, so let me conclude on the interior penalty function method. So we start from initial feasible point. It's important to start from feasible point, initial feasible point, because if we start from the point outside the feasible region, it will not, the point will not evolve to the feasible point. Okay, so we have to start from feasible point first. Okay, feasible point means, well, this point satisfies all the constraints. Okay, and then we select initial value of R1. Okay, R1 is coefficient of that penalty function, and then we minimize the transform optimization problem in the transform objective function, okay, by using any unconstrained minimization method. Okay, and we obtain the solution, and then we test the solution if the optimum solution of the original problems. Yeah. If not, you change the coefficient again. Okay. We change the coefficient again and repeat the algorithm. Once we change the coefficient R, then we have to retransform the objective function. Okay, and we solve the problem and obtain the optimum point, and we check again if we should stop. If not, okay, we repeat it again. Okay, and the next one is exterior penalty function method. For interior penalty function, we use penalty function, which is an exterior function. Okay, for example, the coefficient times with max function like this. Okay, max Tj is 0. Okay, so in the exterior penalty function, see that once we cross the constraint, we add penalty to the objective function. Okay, like this. Yeah, the original problem is here, right? And then once the point violate the constraint, the objective function will change. okay, will be penalty by that penalty function and coefficient r. Okay, if we change the r, I mean the coefficient of the penalty function, of course the shape of this transform objective function will be changed also. Okay, so for the algorithm of the exterior penalty function, okay, we start from any design x1, okay, any design vector. We can start from infeasible point, the point which lies in the infeasible region. It's possible, okay, and then we transform. We transform the objective function by adding the penalty function, right? And this penalty function must be exterior penalty function, okay? With this one, we find the optimum point and then we check if this point is acceptable, okay? By checking with KKT is possible, right? You can check with KKT, Kurach-Kuhn-Tucker, or you just check the feasibility of that point and also, yeah, other indicator, other parameter like convergence rate and so on. And then you change R, right? You change R by using RK plus one, CRK. And then you solve the problem again, you obtain a new point and then you compare with the previous one. If the new point is satisfied, if not, you stop. If not, you have to repeat it. You have to find a new CR, new R, new coefficient, and then find the new point again. Okay. Any question? Any question? We finish everything and then, yeah. No more class on next week, right? And then we have exam on Wednesday.
Sorry, Prof. Are we going to have practical examples?
Of penalty function?
Yes, Prof.
Okay, I will do it and okay, it's okay. I will do it and then I will send you later.
Thank you.
Okay, so the exam is on 7. Okay. Again, it's online. Okay, you have 3 hours to complete.
อาจารย์ส่งสไลด์ล่าสุดให้ด้วยได้ไหมคะ
ได้ครับ เดี๋ยวส่งให้ทางไลน์โอเค
ขอบคุณค่ะ
Anything else? Okay, if not, well, I will stop at this point and then I will send you the slide today. And later I will update it with new example. Okay. Okay, so that is enough for today. Okay. Of course, if you have any questions, you can ask me via line. Mhm. Okay, have a good day. Bye bye, everyone.
Bye bye.
Thank you, Professor. Bye bye.
Yeah.